All right, you already know how to calculate ionic strength, and you also know that incorporating activity into the equilibrium constant is a little better expression than just simply including concentration. And then you also know how to look up the activity coefficient in the table. These are all things that you should already know by now. For this problem, we're not going to do anything fancy like having to make you interpolate from a table or use the Dybye-Huckel equation in order to just plug and chug and get your activity coefficient. So today we're just going to use the simple one that's just going to have a mu straight from the table. But this example is going to show you how you incorporate these activity coefficients into just basic simple equilibrium problems. All right, so to begin with, here's our problem. We want to find the percent relative error introduced by neglecting activities and calculating the solubility of barium iodate in a 0.033 molar solution of magnesium iodate. So the things I would notice first is when it asks you to calculate the solubility of barium iodate, what is it asking you for? Yes, it's asking me for the solubility, but what does that mean? So remember, solubility is basically asking you to find how much of the species that is 1-to-1, okay, with barium iodate. It's asking you to find which species is 1-to-1 with the solid that was dissolved. And in this case, that's barium. So barium is the thing that's going to tell us the solubility. So basically, this question is asking us, what is my concentration of barium if I neglect activities, and what is it if I do this problem the technically correct way and include activities as opposed to merely concentrations? So that's the problem we're going to do. So to begin with, the other thing you should have noticed is that we have a common ion. So both our sample and our salt both contain iodate, which in this case is actually going to simplify the problem a whole lot. If you notice, this KSP is really small. It's 10 to the negative 9. That means that you're not going to have a whole bunch of barium or iodate dissolved into solution. But if you've got a 0.033 molar solution of something that is our salt, we're going to assume this is going to completely disassociate. And so in that case, you're going to have a ton of iodate that's being produced from magnesium iodate, whereas only a small amount is going to be produced by our barium iodate. Now this is important because that's what simplifies this problem a great deal for us. So let's first look at magnesium iodate. So magnesium iodate is going to decompose into our magnesium 2+ ions and 2 iodate ions. So if I first ask the question, what is my concentration of iodate if I started out with 0.033 molar of my magnesium iodate? That means that's going to translate to 0.033 molar magnesium. And since there's a 2 here, you multiply this 0.033 by 2, and we get 0.066 molar. And now that we've established that, we can think about how much iodate is being produced from barium and how much is going to be produced from magnesium iodate. And it's going to majorly be due to this. So if I were to look at all of the iodate in my solution, it should be a mix of my iodates coming from my magnesium and from my barium. But the thing is, my barium concentration contribution is so small, it's going to basically make that insignificant. That's going to be 10 to the minus 9, so you're talking a whole bunch more zeros over here before you finally get a digit. So the majority of our iodate is going to come from our salt in this example. All right, so let's pretend, to start out with, let's pretend that we don't care about the salt. Let's neglect the activities. That's what the first step is. So if I were to do that, I've got my barium iodate, I give you the KSP, and I just simply ask the question, how much barium, so we're ignoring the activity of it, we're not just ignoring it completely. So how much barium is there? So if I were to write my KSP, products over reactants, in which case our reactants is a solid, so barium 2+ times iodate. Don't forget to raise it to the second power because it's got a coefficient of 2. But now I know what my iodate is because I just determined it. If my total iodate in my solution comes mainly from my magnesium, I know this. So I know my KSP, I know my iodate, now I can just solve for barium. I haven't incorporated the activity or the ionic strength in the slightest. I've just looked at direct concentrations. So that means my KSP is 1.57 times 10 to the minus 9 equals barium concentration times iodate concentration, which is 0.066 squared. And that gives me a barium concentration equal to 3.60 times 10 to the minus 7 molar. All right, so this is my concentration if I neglect my activities. But now we want to redo this whole equation, but instead of including my concentrations, I need to include these activity coefficients in my ionic strength. So we've already figured out how much barium is in our solution if we neglect or if we ignore the fact that ionic strength plays a role. We get this amount of barium. Now let's rework this problem, but let's include them. So to begin with, you first want to calculate your ionic strength. You can't figure out your activity coefficients until you calculate your ionic strength. So you have to start there. Mu is 1/2 of your magnesium concentration. So in calculating my ionic strength is 1/2 times the concentration of my magnesium times the charge of my magnesium squared plus the concentration of iodate times the charge of my iodate squared. Now if you notice, the number one thing I hear students ask is, why do I not include barium? Or maybe they use barium to calculate this. Well, remember the analyte is what we're studying. Everything else in solution is my salt. That's going to be my contributor. Also, remember that this is an unknown. We don't know how much barium we know, but we do know it's tiny. And so in thinking that it's tiny, the contribution to ionic strength is minimal. That's why it's our analyte. We're trying to figure things out about it. So here's my formula. Now we got to fill in the math and figure out what our ionic strength is. So if we do the math, we're getting 1/2 times the concentration of magnesium squared, times the charge squared plus the concentration of iodate times its charge squared, and we're going to get 0.099, which is approximately 0.1 molar. And this we can look up in the table. So if we go to our table and look up our activity coefficients, then we get 0.38 for barium, and we get 0.775 for iodate. Now remember, you're looking these coefficients up for your analyte, not for your salt. So now we know our ionic strength, our activity coefficients. We can just plug them back into our KSP equation, but instead of it being K equals concentrations, it's K equals activities. So we now know our ionic strength and our two activity coefficients. And remember, they are the activity coefficients for our analyte, not for our salt. So now we can go and calculate our equilibrium, use our equilibrium constant to calculate our barium concentration, but instead of only including concentration, we can now include these activity coefficients in our K expression. So since activity equals my concentration times my alpha, I'm basically adding in a gamma for every, a gamma. I'm basically adding in a gamma into every single equilibrium expression. So now I've got my equilibrium expression. My KSP equals 1.57 times 10 to the minus 9. That came from the problem. Then barium, that's my unknown. My activity coefficient of barium is known. My iodate concentration is known. Remember, it was 0.066 molar. And then my iodate activity coefficient is we already found as well. Now remember, if it was squared, because it was squared in as a coefficient from our equation, you must square both the concentration and the activity coefficient. Don't forget that. So then next, we can just perform the math and solve for barium. All right, so now we know how much barium we have. It's 1.58 times 10 to the minus 6 molar. And so this is how much if you include the activity coefficients, and this is how much you get if you don't. You may think that's not a big deal, but still, it's a factor of 10. 1 to the minus 6 and 1 to the minus 7. All right, so we get barium ion is equal to 1.58 times 10 to the minus 6, and my neglected value is 3.6 times 10 to the minus 7. That's a factor of 10 off. You may think that's not a big deal, but in actuality, that's a huge amount as far as concentrations. If this were pH, that would be a whole pH unit. All right, so Also something to notice, see how this is -7 and this is -6? That makes sense because if you have more salt in solution, remember it's increasing those ionic radius around these ions in solution, which means your barium and your iodate are not going to find each other as often as just having them in solution. And so now you're increasing your concentration of barium. Okay? So when you take into effect the charge of iodate and the fact that it's a common ion, these are the values, this is the value that you get. When you only take into account the common ion, this is what you get. Both have to be taken into account. If you think about this in medicine, the LOD and the LC50 or lethal dose 50, LD50, if the LD50 and the effective dose are really close to each other, you can't be off by an order of magnitude of 10 because you could kill a patient, and we're against that. Okay? All right, so now percent relative error. Let's work that next. All right, so to calculate your percent relative error, you've got your accepted values here, so it's the difference between your accepted and your experimental, and on the bottom you put your accepted. So whichever one is the more true value, your more correct value, that's the one that goes on bottom. So the difference on top, the true one on bottom, times 100, and we end up with 77.2% error. So yes, really big difference. So I hope you got out of this that including and neglecting activities is pretty much the same process, except for you have to calculate your activity coefficients and include them in the calculations when you're including the activities. But when you're neglecting them, you don't. So in order to calculate those activity coefficients, you just have to calculate your ionic strength and look it up in the table. And then the process is pretty much the same. If you can work normal equilibrium problems, you can definitely work these.